Well, welcome everyone to Filippos' second talk on surf theory and the pseudo-isotopy problem. Load shedding has just happened, but never fear.
The cool thing with not having internet. No disruption occurs.
Okay. So hopefully, let's just check. Shimal, can you read us? And who else is in the audience?
Yes, we got
all good. Okay, great. I think let's start. Thanks.
So there is some
disruption.
Good. Bruce, a question for you. Which you might not know the answer to, but if I minimize the window where it shows my face, will it still be on the recording, or are we going to lose anything?
You can do it and check that. That's the point of having me here, because then I've got what the audience sees.
Right. So that's what I probably want.
So it's fine. So
that's fine.
Yeah.
Okay. So you don't have to see me twice here. Okay. Are we good to start? Is everything?
We're good to start.
We're good to start. Yeah. Okay. All right. So, well, welcome everyone. I just want to start with a small review of what we did last time, and then introduce Morse functions and more things along the way. But just recall from last time, what is the thing that we are trying to study? We're trying to study this space of pseudo-isotopies on a manifold M. So these are, let's see if I can, right? These are diffeomorphisms from M cross I to M cross I. That are the identity on the bottom half. So M cross 0 to M cross 0. Okay, there is a bit of a lag, which is
it'll come.
It will come. Okay, I'll carry on. Okay, and what we did last time is that we constructed this vibration. So I constructed to you a map from this space of pseudo-isotopies to the space of real valued functions, smooth functions on M cross I, sorry, with no critical points. And what was this map? The map would send D it would send D to pi inverse composed with, pi 2 composed with D inverse, where pi 2 is the projection to the second factor. Sorry about the lag. Anyway, so and the fiber of this vibration is a space of isotopies on M. So maps from diffeomorphisms from M cross I to M cross I that are level-wise preserving. That's what we constructed last time. So maybe you want to have a mental picture of a vibration like the one that I'm showing here. But the main proposition that we ended up things with is that if you give me a pseudo-isotopy D, so maybe, I don't know, think of your pseudo-isotopy as like living up here in the vibration. There's going to be a one parameter family of pseudo-isotopies connecting D to an isotopy. So I'm gonna have like a path upstairs to an isotopy if and only if there is a path of real valued functions with no critical points connecting P of D, so connecting pi 2 composed with the inverse to the projection pi 2 from M cross I to I. That's the proposition that we ended with, and that's the proposition that allows us to take the pseudo-isotopic problem and translate it into a problem about smooth functions. And the main theorem now that Cerf proved, which will get to think about is that if the relative fundamental group of Fm comma epsilon of m is trivial, so Fm is the space of all smooth real value functions on m cross I, and epsilon of m is the space of the subspace of the ones with no critical points. And what does it mean? I guess I made a little bit of a schematic here. If you want to think about the relative fundamental group. So every path in f of m, I'm showing you such a path here with endpoints in epsilon of m deforms relative to its endpoints to a path that lives entirely within epsilon of m. So like that. Then every pseudo-isotopy of m deforms through pseudo-isotopies to the identity. Okay, so in particular, any diffeomorphism which is pseudo-isotopic to the identity is going to be isotopic to the identity. And sorry, that's not the theorem that Cerf proved. That's an immediate corollary of the proposition that I just stated. So it's just that because the space of all smooth real value functions is contractible, we know that this relative fundamental group is going to be trivial. That would imply that the space epsilon of m is connected. And since the space epsilon of m is connected, then I would know that I can always have a path from pi2 composed with the inverse to pi2, which would then imply that every pseudo-isotopy on m is equivalent to an isotopy. And I guess what Cerf proved is that if your manifold is simply connected and the dimension is at least 5, then this relative fundamental group is indeed trivial. So that's basically just review from last time. And sorry again about the lag, but is that relatively clear where we left things off, or shall I say more? It's a good place to ask.
Excellent summary.
Okay, so now let's start talking a little bit about Morse functions. So the idea so far is that we got a problem, the pseudo-isotopy problem in differential topology, and we reduced it to a statement about like this relative fundamental group. But reduced here is a little bit of a, like this is still quite hard. I mean, we know that the space of all real valued functions on m cross I is contractible. So like homotopy theoretically, it's like maybe not the most interesting space, but it is quite a complicated space if you want to understand concretely. Like there's lots of singularities that can show up, which are not easy for one to like get your hands on. So what we are going to do is we are going to construct some subspaces. We're only going to see one of them today, but the rough idea is that we are going to construct some subspaces F0, F1, and F2 which live in F, which we can very explicitly understand, and which satisfy like the following properties. The following properties are like our sort of like maybe guiding principles that will tell us that these spaces are useful to us to study. So F0, So F0 will be dense in F of M. So that's like one thing. And then if you look at maps, if you look at paths in the space F0M union F1M, this is dense in the space of all paths in F of M. And likewise, if you look at two-parameter paths, so paths of paths, in F0 of M, F1 of M union, sorry, F1 of M union F2 of M, this is going to be dense in the space of all two-parameter paths in F of M. Right? That's what we are slowly going to build. And what will that allow us to do? Well, it will allow us to, instead of think of all of F of M, instead of thinking of all the smooth real value functions on M cross I, will allow us to just concentrate on this subset F prime of M, which consists of the union of like these three things. And this is like something that we have a chance to explicitly study. That's like the big picture of like where we are headed towards. And this space F0 of M, space of excellent Morse functions on manifold. Well, I guess here there is already a little bit of a yeah, let's say on the manifold M. Yeah, before when I was writing that, I meant on the manifold M cross I, but I am now going to forget a little bit about the pseudo-isotopy problem, and I'm going to think about smooth real value functions on manifolds in general. So I just realized there's this discrepancy in my notation, but please ignore it unless.
Do you define the Fi's of M?
Well, I'm going to define the F0 of M right now. And then next time we're going to define F1, and then the time after we're going to define F2. But and there is something general that one can might say, like, so you can actually build a filtration, you can like actually construct like Fi of M and actually filtrate the space. But we're not going to do that because we don't need it for like our purposes. We just need the sort of like first layers of this filtration. But I'm going to define F0 like
we care about this relative fundamental group. So we get the most maps from cubes.
Yeah.
Or
yeah, exactly.
squares.
Exactly. So if you wanted more homotopical information, you would care about more pieces of that filtration, but exactly. Any other questions, comments, concerns? Okay. So let me just tell you what a Morse function is. So if you a smooth function, consider a smooth function f and take a critical point. What it means for something to be a critical point is that the differential at that point is 0. So if you prefer, choose any coordinate chart that you like around P. And so that condition is that all the partial derivatives with respect to that coordinate chart at P vanish. Actually, maybe I should say, since I got it to be centered at P. And this critical point is going to be called non-degenerate or of Morse type if the Hessian of f at P is non-singular. So just as a reminder, the Hessian is this matrix of second order derivatives at P. So I have this matrix with entries I, j, and a matrix being, I guess, non-singular. I just want the determinant to be non-zero. Sorry, xj. Sorry, yeah. Good, yeah. So yeah, and so that's what it means for a critical point to be of Morse type. And then if all the critical points in my smooth function are of Morse type, then I'm calling the smooth function Morse. And you know, when in mathematics, when you don't really have a good terminology for an object, you usually call it good. Now we're going to call the Morse functions excellent if the critical values are pairwise distinct. So like something that's not excellent.
Well, did you say what a critical value is?
Yeah, but I'll demonstrate with this example. So something that's not excellent is shown in this picture here. I guess maybe I should say yes. A critical value is just the image of a critical point, and here I have this Morse function which is which is the height function. Oops, sorry. It's the height function for this surface here. And I guess I've tried to draw it suggestively so that the two critical points have the same critical value. And that's something that, you know, the critical points themselves are like of Morse type. They're perfectly nice. They have the same critical value. That's also okay. It's just, you know, it's a Morse function. It's just not an excellent Morse function. And the theorem that that we are going to prove today, well, proof is always a bit of a strong word, but I'll give you, I think, lots of reasons to believe in it, is that the space of excellent Morse functions, which is what I'm calling F0M, is an open and dense subset of the space of all smooth real in the C infinity, in the Whitney C infinity, in fact, in the C2 topology. And I'm going to define what it is in the second half of the talk, but for now, just think of there is a topology that you can put in this space, and this theory makes sense. So that's really our goal for today. Yeah.
I'm a bit confused, the last talk we like the FM we were not in the space of functions on M cosine.
Yeah.
And so do you have a way to move from that to this one, or is two different things?
No, we have it's that thing which I realized I started speaking. I made this discrepancy in Okay, that's good. Okay. Thank you. Okay. So, okay.
They're happy. Everybody's happy. And
Everyone's happy?
Yeah.
Amazing. Okay.
And maybe the lag.
Maybe, yeah, maybe that's too, actually. Yeah. So maybe that's too. But are you happy? Yeah, what's that? Okay. And are there any other concerns or questions? Are we good to go? Yeah, good. Okay. Okay. Before I go into what's going into the proof of this theorem, which I think is a very beautiful story that involves small machinery that Tom built. I promise that one of the things that makes these F0, F1, F2 useful is that we can get a very explicit understanding of them. Okay. And up to now, I just gave you a definition. I told you what it means to be a non-degenerate critical point, which is pretty cool, but it's not like you've suddenly become super happy by looking at this definition. There's still, you might hope for being a bit more explicit about.
Infinitesimal definition.
Yeah, exactly. Yeah. So I'd like to make true to this promise that I gave. So we have the Morse lemma, which gives us this quite explicit understanding of what the Morse singularities are. So it says that if P is a non-degenerate critical point, there exists a coordinate chart which is centered at P, such that locally my function takes this very simple explicit form. It's this quadratic form. So I have minus x1 squared minus blah 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 minus xi squared. So this I here is actually an invariant of the critical point. It's the index, and I should underline here. Yes, it's the index of P, and then plus x plus 1 squared and so on. So I want to give a bit of a proof sketch in case you haven't seen this, which I'm not going to give the complete proof, but just a couple of steps into the proof. And the only thing that I want to showcase is where in the proof we are using that this is a critical point, where we're using that it's a non-degenerate critical point, because I think that's useful to have in mind, and then you can recreate the proof on your own. But the sketch is as follows. First, pick any coordinate system around P. So here we're not actually using anything other than M is a manifold. And the thing that we want to do is that we want to find functions. I'm calling them F1 up to Fn. I want to find such functions that would allow me to write F. And actually here, one thing that's a little bit confusing in the way I wrote it. I should use a different name here. So why? Because this coordinate system is not the one we're going to end up with. It's a coordinate system that we're going to make coordinate transformations on. But so my coordinate system is y1 up to yn. And I want to find functions fi that will allow me to write my function f in this form. It's f0 plus a sum of yi times a function that depends on y1 up to yn. And it's actually quite a cool trick. If you haven't seen this, we're using the fundamental theorem of calculus. So I'm going to write fy1 up to yn, f0 plus 0,1 ddt, ty1 up to tyn dt. Okay. So the expression on the right hand side is the same as the expression on the left hand side by the fundamental theorem of calculus. Now, I guess the usual the usual issue when you decide to change notation in the middle of a talk comes to bite you. So I'll try to solve it by overriding. But now I'm gonna use the chain rule. So I'm gonna substitute this ddt by a sum of partial derivatives in the yi's, and now I'm just going to take basically the sum out because my integral only depends on the dt. So anyway, I'm doing this probably in much more detail than is required, so that's what I am ending up with, and I'm now taking these guys here to be my FIs. Okay, so that's, I don't know if that was that made sense, what happened here. But I just, here we haven't actually used anything about P being a critical point. That's true for like at any point in your manifold, you can like you can do this trick. Now we're going to use that P as a critical point. P being a critical point means that all these partial derivatives at 0 are 0. So that means that my ith chosen function at 0 takes the value 0. So now if I repeat, I can repeat the same process for each of the FIs, and I can write down my initial F. I can write down my initial F as this quadratic. It's like F of 0 plus a sum that's now indexed by I and j, yi times yj times another function in the y variables. And now this is the point where I don't want to do this explicitly, but the proof will carry on by basically diagonalizing this quadratic form. And this is where you're using non-degeneracy. So if you try and like, there's basically only one thing you can do when you like, if you try and write down what needs to be done, and you'll see that at some point you are dividing by things which you know are non-zero because of the non-degeneracy condition. So that's roughly how it goes. Are there any questions, comments, concerns? The one immediate corollary of this, which is quite nice, is that all non-degenerate critical points are isolated, right? Because we now, I mean, up to now, I defined them just by what happens, like as Bruce said, infinitesimally, but now I told you what the behavior is in a neighborhood. And so we know from this expression that in a neighborhood of P, there's not going to be any other critical points and of Morse type or of any type. And so if M is compact in particular, we know that it's going to have finitely many. Okay, so if everyone's happy about the Morse lemma, are you happy about the Morse lemma? You're not happy about the Morse
Let me just ask one, because I love the Morse lemma, but I know there's one proof of it called that unit cell called Moses trick or something. Is this, or am I getting confused?
Is that Moses trick?
I'm not sure.
Okay.
But because the last step it's quite interesting that you can, I mean, you can clearly diagonalize the quadratic form at a point, and now you want to do it on a neighborhood, and then you also want to understand that's going to give you new coordinates, a new coordinate system. You gave a beautiful summary, but
there is still work.
It's still some
Is this work something like a sort of algorithm to diagonalize a quadratic form? It's a sort of like smooth invertible operations.
Yes, yeah.
But I guess it's not apparent that well, yeah, maybe it is kind of something like that. Just like, for example, if you have like a sort of like Riemannian metric, you can always,
Yeah,
you know,
fair
you can
enough.
always kind of turn it into, yeah,
Fair enough.
it's some, I
Yeah.
imagine it's some.
Yeah, yeah.
Like,
It is that diagonalizing is like a smooth procedure, and so it's
just like
like
gravity.
Yeah, yeah,
Yeah. But I think that's exactly. But it is something though that still requires an explicit calculation. Like it's not something which I'm very happy to do. Like in the end, if,
That's fine.
I just didn't
Yeah.
want to do it in the
Absolutely,
actual talk.
yeah.
But in the end, we can play
Yeah.
with that. It's definitely instructive. Okay. Any other concerns about?
Just a quick question. So you keep talking about these strata, because these are called strata, right?
Yeah.
As being dense with respect to the Whitney infinity topology. But because we're talking about functions into R, we could also consider them dense with respect to the topology used by, say, the subnorm of functions on R, right?
Yeah, okay. Yes, I think that's right. Yeah.
Are these two versions equivalent?
Oh, that's a good question. Because
Because I think that seems to be introduced with respect to the norm rather than the C infinity. And maybe that's a simpler way of giving
Yeah.
a topology on these functions.
I believe I don't know on top of my
But
head.
Probably, I'm hoping that the direction goes that if that the sort of something converging, well, like let's just say a sequence of functions converges in the Whitney C infinity topology, it implies that it converges in the subnorm, because C infinity is somehow
So-
saying that you converge and all your derivatives converge.
Exactly. Yeah.
Um,
Yeah.
And I don't know what that means about.
But so here's the thing, because the thing that I'm afraid a little bit is that maybe this scene, maybe is the subnorm topology is the would be the C0, because I know density. At least I know that you have density. C infinity is a bit strong, but I think you need at least C2. So
I see.
I don't know. I mean, that's why I said, in
Yeah.
fact, C2. And I don't
I see.
know.
Yeah.
I just don't know on top of my head, like where the subnorm topology.
I think the subnorm topology just loses too much information.
Yeah, I think it's just it just continues. It just treats as continuous functions, and yeah. So I'm afraid that it wouldn't work. I do have quite a bit of an extensive discussion on the topologies that we can put here, but the subnorms didn't make it. Yeah. Okay. Other questions? So I'm not going to explicitly use gradient-like vector fields. They do show up in Cerf's proof and pretty much in everything that you are going to do with Morse functions. But I just felt there's no way you can give an introduction to Morse functions without saying something about gradient-like vector fields. So I just wanted to have a section here where we discuss a little bit about them. And then depending on how much interest there is, maybe we can discuss even more about them later on. But yeah, so I should tell you what a gradient-like vector field is. So if you give me a Morse function, a vector field, which recall is just a section of the tangent bundle, this is gradient-like if I guess the following conditions are satisfied. So psi of f at x is positive for all x that is not a critical point of f. And just recall what I mean by that. We have the derivative map from the tangent space of M to the tangent space of R, and the tangent space of R at any point is just canonically it's just isomorphic to R, and so this derivative map is going to take the psi of x, which is just a vector in the tangent bundle and just gonna give us a real number, which we ask for it to be positive. So that's like one requirement. And then the other requirement is that if P is actually a critical point, then there exists a Morse coordinate chart around P. That's what's given to us by the Morse lemma. And in those coordinates, what we actually want to do is we want to take the gradient of this quadratic function with respect to the standard Euclidean metric. That's going to give us a vector field in Rn, which we then pull back by our coordinate charts to our vector field in the manifold, and that's what locally the vector field will look like in a neighborhood of P. And that's the definition of a gradient-like vector field. Now, this requires discussion. So, and I say, because this troubled me for a very long time, so I wanted to trouble you for some time as well. So, if I ask you to define something called gradient-like vector field, like a reasonable definition that, and I think actually a definition that might be more true to its name, would be the following. It would be a vector field, which is the gradient vector field of F with respect to some Riemannian metric G on M. Okay, you don't specify what the Riemannian metric is, so it's less information, but I don't know, that personally sounds to me like a perfectly reasonable definition.
Just remind people what that means. What is the gradient vector field with respect to Riemannian? So given a Riemannian metric, what is the gradient?
So it's the let's see if I can what do I want? I want to take the inner product. Wait, so where does
Yes, you want to take df and then
yes.
make df into a vector.
df of x is the inner product of something and f. Lower x, and that something is.
Oh, I see. So you could just write here.
You could write the formula, like the.
Sorry, I'm getting stuck here. Sorry, give me a second. I want.
I'll blank that as well.
Wait, sorry.
Just need the inner product.
So you want to write something grad of f inner product grad of f comma x, and that should be the same as x applied.
That's right. So your initial thing shouldn't be applied to B. It should be the inner product of grad gf with B.
Yeah. So grad of inner product grad of f comma x. All the way around.
Sorry, I just I'm blanking out.
The inner products are G of nabla f
comma x.
Where x is arbitrary
X
tangent,
is some other tangent vector.
tangent field.
Is the directional derivative of the direction of x.
Is x applied to f.
Exactly.
Wait.
I'm thinking of x as like a function from real value functions. Tangent field.
This is good. I would instead of saying x equal B, then that thing equals df of B.
Or if you like.
Yes.
Yeah.
Yeah.
Sorry.
Yeah. No, cool. Good.
You're thinking of the derivation.
df applied to D is the same as D applied to F.
Yeah, sorry. And well, anyway, yeah, I basically just want to ask the question of, does definition 1 imply definition 2? And what about the other way? And like, namely, does definition 2 imply definition 1? I don't want to give you an answer. I want you to think about it, and we can discuss about it later. But does the question make sense?
I think if you gave the traditional name for what you call a gradient vector field originally, that might also be real.
Yeah.
Yeah, so you're right. But
sure, yeah. But okay, so I'm just gonna leave that aside, and we can go back to it. No, I just wanted to maybe sketch an argument as to why every Morse function admits a gradient-like vector field. There are, and the proof basically goes as follows. There's 2 cases to consider. One case is if f itself has no critical points. If f itself has no critical points, I guess I won't really justify this, but locally I can always find a coordinate chart centered at P, so that f will locally look like f of P plus x1. Yes, that's one of the conditions of being a submersion at P. And that follows by the implicit function theorem, but let's not go there. Now, we took M to be something compact, so there are finitely many charts that I have like these, and in each of them I can choose the vector field 1, 0, 0, 0, and then glue all of these vector fields together using a partition of unity. So I don't know, pictorially, if you wanna think about it, if f has no critical points, then my manifold is going to be like a cylinder with this height function, and I guess I have the coordinates x1 and x2 in a coordinate chart here, and that's what my gradient-like vector field is going to look like in this coordinate chart. And now, if f has a single critical point, what I'm going to do is I'm going to choose a Morse coordinate chart around this critical point, and I also want to choose an open subset U bar in U. Now, the complement is going to be compact, so then I can just run stage 1 again. So I can find a gradient-like vector field in the complement of U bar. And then in U, I can use the vector field that I get by pulling back the standard vector field, sorry, the gradient vector field with respect to the standard Euclidean metric of this function. I guess if you want, here is a small pictorial representation, but now I have 2 things that I can glue together with a partition of unity, and I get a vector field which satisfies the properties that I promised you. And the I guess the important thing in the story is that Morse functions with associated gradient-like vector fields allow us to reconstruct the topology of manifolds. It's not something that we are going to see explicitly today. I'm happy to talk more about it next week or like some other time. But that's really the key extra data that one associates to a Morse function to get information about the manifold that you began with. And the thing that I now want to talk about is the, I guess, genericity of Morse functions results that I promised. But are there any questions, concerns, comments? Okay, maybe we can postpone the break because we had a bit of a break with a connection. So maybe I can go on, even though that like now it's actually a good time for a break. But let's first define maybe what gen bundles are, and then we can take a break. So if you give me so first I'm going to give you a bunch of definitions, and then everything's going to come together. But maybe for a little bit of time, it might seem a little bit dry, but we'll try to motivate as much as possible. So if you give me smooth manifolds M and N, I want to first define what a germ is. So a germ of smooth functions between M and N based at X. Well, that's going to be the data of an equivalence class of pairs. The pairs will be a neighborhood of X in M and a smooth map from that neighborhood in N. And what's the equivalence relation to such pairs will be equivalent if there exists, well, some open in the intersection, some open subset of the intersection such that F restricted to V is equal to F prime restricted to V. So I guess the idea is that you only want to keep track of what the function does in the neighborhood of your point. In fact, you don't even require the function to be defined away from a neighborhood of your point. And then a K-jet. So everything here was, continues. Now we are going to add differentiable data to it. So a K-jet with source M and target N will be an equivalence class of triples now. So the triple is going to be X sigma Y. So X is an element of M, Y is an element of N. Sigma is a germ such that sigma of X equals Y. And two such triples will be equivalent if, X equals X prime, Y equals Y prime, and all partial derivatives up to order K of sigma and sigma prime at X agree. Okay. And now J upper K of M comma N. This is going to be the set of all K-jets from M to N. I want you to take by belief that it has the structure of a smooth manifold and that the projections, So there are evident projections to M, to N, and to M cross N, and they're all fiber bundles. We can discuss more where does the structure of a smooth manifold comes into play. But that's at least, that's the very basic construction that's going to come up to what we're doing. Is the construction clear, like what this space is, what a K-jet is, and what a germ is, if you haven't seen it before?
It's elegant, but it is an infinite dimensional fiber bundle.
No, it's not. It's a smooth. It's actually not infinite dimensional. No. I don't remember the dimension top of my head, but no. So the way because the
Maybe that dimension should be like
You'll be adding another coefficient.
exactly. Yeah, exactly. So like exactly. So JK of RM comma RN, maybe if you wanna look at a chart. So that's going to be RM cross Rn that chooses a point in RM and a point in Rn. but then the differential,
Themselves are
right.
infinite.
and then but then the differential is completely determined by like a Taylor polynomial truncated at level k. So you basically add all, you need to like just multiply by the space of degree k polynomial functions from Rm to Rn, which is finite dimensional.
I mean, maybe it's kind of also as an example, you can like relate this to the, let's say, the cotangent bundle, and you can see why like adding extra derivatives, right? And what's J? What is there some relation with like some one jet bundle and bundle of one jets? Isn't that like the cotangent? You can
Yeah, there is
something like that.
yeah,
Right.
exactly.
And
Yeah.
sort of just takes into account first order derivatives.
That's
Higher order derivatives are never going to give you like infinite.
exactly. I think I mean, it's like a relevant remark to like what you said. Like, I just wanted to maybe say is that yeah, if you look at the I guess fibers of the first jet bundle, yes, that would be hom txm tyn. That's something that I can identify with from Rn to Rn. So it is a vector space. I just wanted to make this sort of like attention remark. It's not even J1, it's not actually still a fiber bundle. It doesn't have the structure of a vector bundle. So I can identify each fiber with a vector space, but I can't do that in a canonical way. So these identifications don't give me a vector bundle structure on J1. It's something that I can do non-canonically at every point, but I can't do more than that.
It's probably even for reasons of like a Taylor series, right? Like in the sense that what the first thing you have sort of just x, xi multiplied by some function. This is like linear, but higher up you have like x squares and squares.
That's right.
It feels like J1 should be a vector bundle, like J2 and J3 maybe will be fiber bundles, but
I don't think
okay, fine.
I don't think
Okay.
because I don't think it's I think the problem is with just so I think what you said is an issue about J2 and J3, if I understand correctly. But I think what I'm even this identification is no. No, you don't think so?
Well, I mean, so if you just have, no, I guess
Let's chat about it later.
Yeah, I think that all I'm trying to say is that when I'm writing down these identifications, I can do them over a point. I can't do them canonically.
Okay.
Over a chart.
I see.
So that's that's the source of the problem here, as I understand it. Would you like to take a break now before we go to the Whitney topologies, or would you like to carry on?
Let's take a 10-minute break.
Yeah. You quickly show me the definition of JK again, please.
Yes. I guess you may want the definition of a K-jet.
Okay.
Because JK is the collection for K-jets. I'm going to mute myself for the break.
Wait a second, I wasn't sure.
sort of, and you just could appease it. I don't think it doesn't link to anybody else.
Okay. Okay.
Okay, great. I'll close the door.
Yes.
Policy.
Going to the with apologies. Yes.
Are we unmuted again, right? Yeah.
Yes, we are. Do you want to say something that requires us to be muted?
No,
Oh,
no.
okay. Okay. Yeah. So I just want to take the time to define the Whitney topologies. And well, again, I won't be super precise, but anyway, so we want to define a topology in this space of C-infinity functions from M to N, so that we make precise the notion that Morse functions are generic. And by generic, typically I will say that a subspace of a topological space is generic if it's open and dense. So I'll be using those kind of interchangeably. And I guess it's useful first to like wonder a little bit about what kind of topology we can put on mapping spaces, because C-infinities M, N is an example of a mapping space. Well, the first one that maybe one sees is the compact open topology. How is that defined by? So the subbasis for the space of continuous maps now from X to Y, subbases would consist of these N, K, U, which are sets consisting of all maps. That's maps from X, Y, such that f of K lives inside U, where K in M is compact and U in N is open. I'm just defining a topology with this subbasis, and that's a nice topology to consider. So there's a remark: if you work with nice topological spaces. So I guess the usual candidates for that is compactly generated weakly Hausdorff. Would you want me to remind you what those are, or are you happy to think of just nice spaces? Good. I left a little bit of empty space in case someone is like, please tell us. But I'm thankful that no one asks me to. Yeah, so category of nice spaces, it's enriched using this compact open topology, and we basically get a tensor homojunction. Like that's one of the reasons why we restrict attention to nice spaces. The upshot is this is a good topology to consider for mapping spaces. That's all I want to say. And well, we want to construct a topology on C-infinity of M, N, and more generally on CR of M, N. So by CR, I just mean the space of functions from M, N that are differentiable up to order R. So they're not smooth, but we can take up to order R derivatives. And well, what can I do? I can, well, one first like naive attempt is that I can use a subspace topology. So I have CR of M, N. Well, this is a subset of the space of all continuous maps from M to N. And this right-hand side guy is equipped with a compact open topology. I can just take the subspace topology. That's not a good idea because we throw away lots of interesting things that we want to keep track of. So we completely throw away all of differentiability data. So we want to do something better than that. Okay. And well, because the second attempt will be more successful. The first thing to like see is that if you give me a CR function from M to N, that defines for me a section of this fiber bundle. And so I'm just gonna, well, let me use a different color. Calling it JRF. And is it clear how this section works? It's gonna basically send like a point M in like the triple, which is M, comma, the germ of F at M, comma, F of M. That's how I'll get it. So what this defines for us is a map of sets, right? So if it's a map of sets for now, but because I haven't told you anything about this topology here. So I have a map of sets from the CR functions from M to N to the space of sections from M to the space of sections of this fiber bundle. Now, this right-hand side, the space of sections, this does have a topology that I can naturally define because it is a subset of the space of all maps from M to JR M comma N. Okay, so I can just use a subspace topology here. Now, there isn't just a map from CR of M comma N to the space of sections. Like this map is an inclusion. So I can realize it. I can realize CR of M comma N actually as a subspace. So just to see the inclusion bit, I have a map going the other way around. What does the map do that goes the other way around? It takes a section. So that's a map from M to JR. Oops, sorry. M comma N. Well, it just precomposes with the projection at N. Right? Remember this fiber bundle. And that is, and this map is inverse to JR. Is that clear? That's, well, yeah, that's basically just because of
it's the thing about you're uncoupling a function from its derivative, right?
Yeah, exactly. And I guess, and we know that we will be, I guess, yeah, that defines what the function is set theoretically, but we also know that it's going to be CR because we know that it came from JR. So we know that I can take at each point up to order R derivatives. And so anyway, the upshot is that JR is an inclusion. So I can equip CR of M comma N with a subspace topology, which is what we'll be calling the Wick-Whitney topology. That's my favorite construction. I mean, there's like, you can also like construct this with like a basis, but I kind of like this way of thinking about it. Yeah, I agree. Yeah, exactly. Yeah.
Well, I mean, the question is though, how hard is it to construct the topology on the jet? It's the space of the jet. So. Yeah,
so I'm definitely throwing things under the rug here. So I take as a given that this space of jets has a topology. It's not. It's not too hard. Like I think, like what we sketched earlier as to why is this like a manifold. it's not too far away from what you would have to do to prove that it is a manifold. And yeah, I mean, there are details, but like this JR space, really, you can give charts which look like Rm cross Rn cross, like the space of polynomials from Rm to Rn. So everything there is like, it has a natural topology, it has a natural manifold structure, and yeah, there is some work, but
can you relate? I mean, you might have this later on, but is CR like Rm to Rn some usual like topology of convergence?
Yeah, there is, but I don't have that later. I can't
you should be able to construct CR and N by just kind of choosing covers for everything, and then like, you know, and then sort of just defining the topology locally and then say everything glues.
I believe that's doable.
Mm-hmm.
Yes.
That's like
I just I just kind of chose like my favorite way of thinking about it, and I didn't think about other ways much. And
you give a bundle theoretic way of thinking about it.
Yeah, I was like,
always a prover.
Yeah,
everything is a bundle, and everything else is a section of a bundle.
That's
Okay.
Yeah, exactly. But yeah, there's definitely more ways one can be more explicit about this stuff. Okay. And then, okay, once you have these topologies on CR, we can get a topology on C infinity. So it's like for any R, I have an inclusion from C infinity to CR. And I'll just define the C infinity topology to be the closest topology that makes all these inclusions continuous. Yeah, so, you know, it's not, the definitions that I gave are not explicit, but I really like them because they tell you sort of like how things need to be defined, and for formal reasons, you know that this is enough to say, and that's all we'll care about. But are there any questions or concerns about the way we define topologies? We have time, so feel free to jump in at any point. Well, if not, then I told you, okay, to what the topologies are, I promise that I'll tell you that with respect to this topology, the space of Morse functions is like generic. I need to give you a tool to like get your hands into such a theorem, because at least a priori doesn't seem like an extremely approachable thing. So the tool is going to be this theorem of Thom's jet transversality theorem. Well, okay, the crucial notion is the notion of transversality, which has everyone here seen transversality, by the way? Okay, perfect. Okay, good. Because I prepared a bit about it, and I don't want it to be in vain. So yeah, so the at least the intuition is that we want to have we want to define a way where manifolds intersect in a nice way. And nice is one of these super dangerous words in mathematics, but I guess at least like an intuitive picture to have in mind is, if you give me a circle in R2 and you give me a line, this is an intersection that I want to think of as nice. This is another intersection that I want to think of as nice, well, namely no intersection at all. And this is an intersection that I don't want to think of as nice. which is like the tangent. And the intuitive picture is that if you give me a nice intersection and I perturb it a little bit, I haven't changed the number of points that in which the two things that I care about intersect. So if I take this line and I perturb it a little bit in R2, I'm still going to be intersecting the circle at 2 points. If I take this line and I perturb it a little bit, I'm still going to be intersecting the circle at no points. But if I take this line here and perturb it a little bit, depending on how I perturb it, I might intersect at 0 points or at 2 points. So I've actually, so this isn't in general position. Is one way would say it, whereas these things are in general position. Okay. And so the precise definition, which I'm going to give for smooth functions, if I have two smooth functions, so one goes from M to W, the other goes from N to W, and I have a point in M and a point in N, which are so that f of M equals G of N. So I have an intersection at W of F and G. We say that this intersection is transverse, and I guess that's the notation for it. If the following condition is satisfied, if I look at the image of the tangent space of M at M via df, and I look at the image of the tangent space of N in N via dg, that's going to give me my entire tangent space of W at W. It's yeah, you can maybe see like in those pictures, like I don't know, if you take the direct sum of those two vectors, they're going to give you the entire tangent space of R2 at this red point. But the same doesn't hold true here because a function intersects the submanifold transversely, which is a notion that I want to show once we.
Because of the definition, I suppose they also intersect transversely if they don't intersect at all.
Well, that's the vacuous case of that definition, yeah. So, well, no, because I told you what it means to intersect transversally at a point. So that requires them to intersect at that point.
You'll find run out of battery.
No, actually, it's a bit, but you seem to have,
Yeah.
the seminal is running, it's just died. It seems like the iPad is
Okay.
connected.
I think yeah, I think it
Yeah.
came back, yeah.
Yeah, Filippos definition, if f of M equals G of N equals W.
Yeah.
If they're equal, then they intersect transversely. Does that mean that if it's not equal to G of N?
I will answer your.
That the result is accuracy.
But I think your concern is, and well, do let me know if that's not your concern, but I think your concern shows up when you think of the definition of a smooth function intersecting a submanifold transversally. So, so let me give you one more definition. And
I can see your screen. I'll probably want to take it so this.
okay, sorry, that's a good shout. So share content. Yes, the screen sharing stopped unexpectedly. So hold that thought. Let me give you one more definition, and then we'll see if there's still an issue. But so if you have a smooth map and you have a submanifold of W, then F will intersect N transversally at that point. If again, it's the same condition. If I look at the image of the tangent space of X at M, and I look at T of F of X of N, then that gives me the whole tangent space of W at F of X. And we say that F intersects N transversally if F intersects N transversally at all points in the pro image F inverse of N. Now, if the pro image F inverse of N is empty, that's a vacuous condition. And so F will intersect N transversally.
Can you just go to the previous definition?
Yeah. So here I'm telling you, in this definition, I'm telling you what it means for F to intersect G transversally at a point in which they intersect.
So the pictures you drew right above that definition really pertain more to the second bit, right?
Yeah.
Okay. Because there's not a nice way of interpreting like the second picture there in terms of this first definition.
Well, I mean, you can say you can say the following thing. You can complete this first definition in the same way that I completed the second definition, and say that F and G are going to be called. We will say that F and G intersect transversally if they intersect transversally at each point in which they intersect. And then vacuously, it would follow from there that if they don't intersect at all, then they intersect transversally. But the way
I mean, you probably have to do a bit of extra data, like F and G intersect transversally at like M and W, F blah blah blah, and and then just say for all pairs such that.
Yeah,
that's cool.
Was there a problem with people? No, everything's okay.
I was just inviting Audrey to dinner.
Okay. Anyway, so and I guess one of the things that transversality buys us is that if you have a map which is transverse to a submanifold of W, then looking at the pro image of that submanifold actually defines a submanifold of M. So, and more is true. We know what the codimension of that submanifold of M should be. And it should be the same as the codimension of N in W. Okay. So we don't only know that. I mean, I just wanted to give an example where this fails if you don't assume transversality. So if you take R3 and you take this plane and you look at an embedding of this saddle in R3 that is tangent to the plane at the sample point, then the pro image of the plane is just going to be these two lines intersecting, and that's not a submanifold. That's like one ways in which this fails if we relax the condition. And an important thing to keep in mind is that one of the things that this theorem implies, this identification of the codimensions implies, is that if the dimension of M is actually less than the codimension of N in W, then the only way in which F can be transverse to N is if it doesn't intersect at all. So it's so I think like the punchline here is that whether two submanifolds or like whether a map is transverse to a submanifold highly depends on what the ambient space is. Like if I looked at, you know, like this line in R2, it transverse the circle, it intersects the circle transversely. But if this instead lived in R3, the same line, that wouldn't be a transverse intersection. The only way I can have a line intersect the circle transversely in R3 is if it does intersect at all, because I have more room to just push things away in R3. Okay. Yeah, so transversality depends crucially on the ambient manifold. And now we are ready for I guess our main theorem. So Thom's transversality theorem, but I should pause for questions. Are there questions, comments, concerns? All good. So okay, so if you give me M and N smooth manifolds and W is a smooth submanifold of the K-jet space of M, N. Now I can define TW to be the space of all maps, C-infinity maps from M to N, such that the relevant section JRF intersects, oops, here that's wrong, intersects W transversally. So this is just a collection. This is just a collection of maps. And Thom's transversality theorem is that this collection of maps is going to be open and dense in the space of C-infinity functions from M to N. Which is quite strong because we have lots of choice here. We can choose the K, we can choose the W, and we can set this up. So then, just to give you an idea, for Morse functions, we get to apply this in the case when N is R. And in the case when W is, guess what's usually denoted as S1, it's a subspace of J1 M, R. It consists of all those jets that whose derivative at the point X is 0. And there are two things that come up here. So one is that S1 is a submanifold of J1, and actually the codimension of S1 is equal to the dimension of M. And then the other thing is that if P is a critical point, then well, okay, the first thing that we have to sort of like note is that if P is a critical point, then by the way I defined S1, if I look at the inverse image of J1F of S1, P is going to be in it, okay? Because P is a critical point if the derivative is, you know, if the derivative of F at P is 0. And the observation is that, P is non-degenerate if and only if J1F intersects S1 transversally at P. That's actually an alternative, well, first of all, it can be an alternative definition of what a Morse function is. So you can say that a Morse function is a smooth function whose first jet section intersects S1 transversely. That's how I want to think about it. It's my favorite, but maybe not the the first one you would see. And also it gives you an alternative proof that non-degenerate critical points are isolated, because remember we have this codimension of S1 equals the dimension of M. So that means that the pro-image of S1 under J1F, well, that's going to be by transversality a submanifold of M, and it's going to be a zero-dimensional submanifold of M. And well, being a zero-dimensional submanifold means that it consists of isolated points. I'm actually ending early. This went faster than I was expecting, which I guess is not bad. But this, just ending with some references here. But that's what I had to say.
Yeah, I'm just thinking. So now you have a new definition of Morse functions.
Well, I think it's up to you what the starting point is. So one can define a Morse function to be that, and then prove that this is an equivalent definition. So prove that every critical point of such a function is non-degenerate, and then use the Morse lemma to give you the local coordinates. That's one way to go about it. Usually you would probably start with giving the definition of what a non-degenerate critical point is, and then show that that's a starting definition, and then it's equivalent to this one. And so this one makes it easier. This one makes it easier to understand why Morse functions are generic, and the definition that we gave initially makes it easier to understand what their local behavior is. It's like, but you kind of like need to know both.
I mean, you can prove that most functions are like generic.
You can also
It's
do
pretty,
it.
I mean, it's pretty like.
You can.
I've seen it in, like,
You can.
Like Orden and.
Definitely, yeah. You can do it by hand without using Morse-Cerf transversality.
Can you explain the remark again? The proof of the
So the I guess let me go back to. Do you is that a theorem that you believe? So if I give you, I mean, I'm not going to give you proof it, but at least the statement makes sense. So if I if I give you a smooth map, and a submanifold of the target, the F inverse, like the pro-image of that submanifold, I mean, usually it's not going to be a submanifold of M, but if the map happens to intersect the submanifold transversally, it is, and we further know what its dimension is going to be. Well, we know that.
Honestly, you were saying that the codimension then is being.
So the codimension is just right. It's like dimension of M minus the dimension of.
Yeah, I'm talking about in the remark now.
F inverse N. That should be an N here. Sorry.
So in the remark, we assume that it transversely intersects S1.
Exactly. So J1. So we know we assume that J1F intersects S1 transversally.
Yeah.
And I'm saying that, well, we know. No. I'm stating it as a fact that the codimension of S1 in J1 actually equals the dimension of M.
So then the codimension of the J1 jet bundle, sorry, the J1 section is also M.
The
Sorry, do we not need J2 somewhere? I mean, it's not the generosity has to do with the hash.
yeah, but that you do if you unwind what it means for J1F to intersect transversely, that if you unwind that, it requires J2 information. So that's where
Right.
so it's in the transversality of the intersection where J2 will come up.
Oh no, I had the definitions messed up in my head. I mean, of course, we keep track of the whole smooth function just as part of like the points happen to just be equivalence class are taking into respect to the first thing that they could be.
Yeah.
S1
Right. So this codimension. What is the definition of the codimension of S1? This is dimension of J1 minus